Having considered the summation operator sigma in a previous recording, we are now going to turn towards the sample variance. In a previous recording, we used the summation operator to derive the sample mean x bar. And remember, that is, so the mean is one of the measures of location, along with the mode and the median. However, apart from the measures of location, we also have the measures of dispersion, which consider the spread of the data. So here we are going to look at computing the sample variance, which I'm going to denote by s squared. Now, if you turn to your subject guide, you will see that there are different formulae that we can use for the sample variance, all of which are equivalent, but depending on the particular information you're given in the question, one form might be easier to work with than another. Okay, so what are these forms? Well, these formulae will all use the summation operator sigma, so we can re-emphasize the work we did earlier. So the first one would be like this. We take the sum, not of each observation, but the sum of the squares of each observation. Again, we have this index of summation I, which goes from 1 to n, so we consider all the observations in our sample. We subtract the following: the sum of the xi's, where I goes from 1 up to n, all squared divided by n, and we divide all of this by n minus 1. So you can see here that we've used the summation operator twice. However, do notice, okay, just to emphasize once again, over here we are not taking the sum of all the xi's, we take each xi observation. I goes from, notice here, 1 up to n. We square that observation and we take the sums of all of these squared observations. Okay, so this equation, I said there are other ways of writing it, and indeed there are. Another one is to say we have 1 over n minus 1 times the sum of I equals 1 to n of the following, xi minus x bar all squared. So again, just to emphasize, what does this mean? Well, for each value of I from 1 up until n, we take the ith observation, so this bit here, xi, we subtract from it the sample mean x bar, okay, so this term here, which typically you would have likely to have already computed. So we do xi, so for example x1 minus x bar, square that value, and then move up to the next value of I and work that out. So this will be x2 minus x bar all squared. So just to write this out in more depth. So this summation here corresponds to x1 minus x bar squared plus x2 minus x bar squared plus dot 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 plus up to the nth observation xn minus x bar all squared. Okay, so we can use the summation operator to consider various functions of the xi observations, as we've seen here. There's one other formula that we could use, equivalent formula, and that's the following. We take the sum of the xi squareds, where I goes from 1 up to n, minus n times x bar squared divided by n minus 1. Now, I'm going to leave this as a little exercise for you to see if you can work out. You can see that this equation here looks fairly similar to this second one down here. You can see we have the same sum of the xi squared terms here, so here and here. We're dividing by n minus 1 here and here. So clearly this term and this term must be equivalent, i.e. that nx bar squared must be equal to the sum of the xi, I equals 1 to n, all squared divided by n. So as an exercise, see if you can work out why this result holds. And as a hint, think of multiplying the right-hand side by, so times the right-hand side by n over n. So you're just multiplying by 1, so the right-hand side remains unchanged. But just have a play around with that if you can see how that works. Right, so considering the very simple data set we had in our previous example, And just to remind us of what that was, we had x1 was 3, x2 was 5, x3 was 1, x4 was 7, and finally x5 was equal to 6. Plugging all these numbers in, if you take the sum of the squares of all these observations, so remember x1 squared is going to be 3 squared, x2 squared is going to be 5 squared, x3 squared is going to be 1 squared, etc., etc. And this all works out to be the following, that the sum of the xi squareds, where I here goes from 1 up to 5, because my sample is of size n is equal to 5, and we'll add all of these up and you will get 120. So plugging these numbers into our equation, let's pick this first form up here. So the sample variance s squared will be the sum of the xi squared, so 120, minus the sum of the xi's, well 3 plus 5 plus 1 plus 7 plus 6 gives me 22. So 22 squared divided by n is 5. Divide this by n minus 1, so 5 minus 1 gives me 4. Plug that into your calculator, and this gives you an answer of 5.8. So for this data set, the sample variance is 5.8. However, you may also have heard of the measure of dispersion, which is the standard deviation. What we've computed here is the variance. What is the standard deviation? Well, the standard deviation is simply the square root of the variance. So we might denote S to be the sample standard deviation, where S is just going to be the square root of the variance, so the square root of S squared. So if you wanted the standard deviation of this data set, you're just going to say that S is equal to the square root of 5.8, and work this out to be 2.4083. So this is your sample standard deviation. So be clear from an exam question, if you're asked to see whether you're asked for the variance or the standard deviation. If you know one, it's trivial to obtain the other. You would just square root the variance to obtain the standard deviation, or square the standard deviation to obtain the variance. But make sure you use the, give the correct form that you're asked for. Why would we prefer one over the other? Well, typically we would prefer to work with standard deviations rather than the variance. And a quick reason for why is to think of the units of measurement. Suppose this data set down here, so the 3, 5, 1, 7 and 6, these related to the level of income, let's say in tens of thousands of pounds per year. So for example, the first individual earned £30,000 a year. Those units are in pounds. If I deal with variances, we can see that when we've dealt with variances, we've looked at squared values. So for example, in my top formula here, we had squares involved here. If you square pounds, you get in units pounds squared. Let's just go over here. Pound squared. Well, I don't know about you, but I've no idea what a squared pound looks like. Okay, so particularly for currencies, a squared pound has no real practical meaning. But if I square root the variance, then I also have to square root the units of the variance. So the variance is given in pounds squared, then standard deviation will be given in the square root of pounds squared, which is just pounds. I know what a pound looks like, so that makes more sense. So usually from the units of measurement, typically we will prefer to work with this standard deviation. So review your subject guide, look at the different equations for computing the sample variance. There are many equivalent ways of doing so, and just have a practice with some past exam papers at computing variances. You can also obviously make up your own very simple data set and compute a sample variance for that. One very final important point though is that variances, and therefore also standard deviations, must always be positive values. You can never obtain a negative variance, or indeed standard deviation. Why is that the case? Well, looking at the three formulae that we've been given here, you can see that they all involve squares. If you square any number, be it positive or negative, you will always end up with a positive number, and therefore by construction the variance or standard deviation will always take a positive value. So if you find yourself computing a negative variance or negative standard deviation, then something has definitely gone wrong. So go back, retrace your steps and see where the error has occurred. Okay, so you can just do this quick feasibility check, make sure that your variance or standard deviation is indeed positive.